In this video, we're going to explore the pressure forces exerted on an object submerged in a fluid. And again, we are still dealing with fluid statics. Okay, so these are fluids that are not moving. They are not flowing. We will explore forces on planar and curved surfaces. Now recall that for a fluid at rest, we know that the force is perpendicular to the surface since the pressure force exerts no shear. Okay, so if we have a surface that is, let's say, inclined like this, the pressure will be acting normal to that surface. Let's consider a general case of an inclined plane that is submerged in a fluid, as shown in this schematic. So now a few things to point out before we begin. We're expressing all pressures as gauge pressures, so this is relative to the local atmospheric pressure. So again, I point this symbol out to you, this triangle on the free surface, which indicates that that free surface is exposed to atmospheric pressure. The solid surface makes an angle theta with the free surface. We let the origin be at the intersection of the free surface plane, being this one that I'm highlighting right now in red, and the plane of the solid surface, being the one at an angle theta. So our origin is at this intersection here. We are looking at this surface from the side. So the surface here, this is a side view, and this surface here is the same surface as the one we are seeing in this side view here, but here we are looking at it head on. Now let's have a look at our coordinate system. So note that y here is expressed relative to our origin of at the free surface. Okay, so this here is y equals 0. And the questions we would like to answer are, well, what is the total force on this surface that is submerged in a fluid? Once we know that total force, we're also interested to know where that total resultant force is located. So, keep in mind that we have an inclined plane, and the pressure, so if we have a free surface over here, the pressure is increasing as we move down in the fluid. Therefore, the pressure force is not uniform on this surface, but rather it is a distributed force. And so what we are saying here is, well, what is the resultant force? So what is the equivalent single force which has the equivalent magnitude as this distributed pressure force? Okay, and this is shown over here in our schematic. Okay, so what we do is that we consider a differential area on the solid surface. This differential area is shown over here and over here. At any depth h, this differential area will have a force acting on it of dF, which will be equal to gamma h. So recall that rho g and z, here we're using h as the depth of the fluid. And then, so this is our pressure force, and then we need to multiply it by an area, which will be dA. So on a small element on the surface, this is the differential force. And this differential force is shown over here. Again, just to note, this differential force is perpendicular to the surface. The magnitude of the resultant force can be found by taking the summation of all these differential forces over the surface. So this summation takes the form of an integral. So the resultant force, Fr, is equal to the integral over the entire area of the submerged surface of gamma h dA. Now, as we move along this surface, h is going to change as well. So the depth h below the free surface is going to change. It makes more sense to express it in terms of y. Okay, so we've set up our coordinate system over here. So we can express h as y sine of theta. And why this is useful is because y, our coordinate y, is aligned with our plane surface. Okay, so I'm just going to write here for clarity that y, so h is equal to y sine of theta. So for a plane surface, which is what we're looking at here, theta will be constant. In addition, we can make a fairly reasonable assumption that gamma, which is related to rho, the density, will be constant. Okay, so this would be applicable for something like water or whatever, especially if we're not looking at massive variations in height. So therefore, gamma and sine of theta can be taken out of the integral. And we are just left with gamma sine of theta multiplied by the integral of y dA. You might have encountered the integral y dA before. This is called the first moment of area. And this is the first moment of area with respect to an axis. And this axis is passing through the origin of 0. Furthermore, this moment of area, this first moment of area, is related to the centroid of the object that is submerged. So the location of the centroid, yc, is equal to the integral of y dA divided by the total area. Okay, so this is kind of like a weighted area. And so these are geometric properties. You probably have seen this before at some point. Okay, so the location of the centroid of the submerged body, and again, note that this yc is relative to our origin, so where the y-axis begins. It is equal to the integral of y dA divided by a. So we can express our resultant force as gamma sine theta multiplied by a and yc. So this is one form of this resultant force that we are seeking. Another form would just be to express it in terms of the depth under the free surface. So yc sine of theta will be equal to hc multiplied by a. And this HC is the depth below the surface where the location of the centroid is found. So we can either express this location as, sorry, I just noticed that I made a mistake here. This is FR. So we can either express it in terms of HC, so the depth below the surface, or YC, which is the distance along the plane from the origin. So although the magnitude of the resultant force is a function of the centroid, the location of that force does not pass through it. And this is a very important thing to note. So the location of FR does not pass through the centroid, which we can denote as YC, if we will. Okay, so let's find the location of FR. This location is denoted in our schematic as YR. R for resultant, so the location of the resultant force. The moment about the origin due to FR will be, so let's just write this, the moment about O is equal to FR multiplied by YR. Recall that FR is due to a distributed pressure force, as shown over here. That is, it is simply the effective result of a bunch of small differential pressures. Therefore, the moment described over here must be equal to the moment due to the distributed pressure force as well. So how would we express that? So what we have a bunch of small differential forces on these differential areas, and each one has a moment arm of y. And we would integrate this over the entire area. So the left-hand side here, so the moment due to the resultant force must be equal to the summation of all the individual differential forces. So we can express this right-hand side, so we know what dF is. dF, we expressed it up here as gamma h dA. So let's write this out again, so FRYR. And let's express h. Recall that h is y sine of theta. So we have gamma sine of theta y squared multiplied by dA. And again, this integration is over the entire area. So what we are looking for is this YR over here, the location of the resultant pressure force. Now what we can do is substitute what we know about FR. So we found FR to be equal to gamma sine of theta multiplied by the area multiplied by YC. So let's substitute this in. We have gamma sine of theta a YC multiplied by YR. And this will be equal to So gamma, we are assuming, is not changing over the area. Sine theta is a constant, so we can take this out of the integral. And so we have the integral of y squared dA. So we note that sine of theta cancels out, gamma cancels out, and so we can solve for yr, which is equal to the integral over the area of y squared dA divided by the location of the centroid multiplied by the total area. So this is the expression for the location of the resultant force. So as you can see, it does not pass through the centroid, but it passes through a point that is related to the centroid, but it is also related to this quantity over here. This quantity is called the second moment of area. And this is called the second moment of area, and we denote it as Ix. So it is relative to some axis, and this is relative to the x-axis. So the x-axis is the axis out of the page passing through the origin. Okay, so if we're looking at our submerged body head-on, we will have an x-axis like this and a y-axis like this. So we are carrying out the summation of all y squared dA, and all of this, these y locations are with respect to the x-axis. So this is why we denote it as Ix, the second moment of area with respect to the x-axis. You will also encounter the second moment of area in your mechanics of solid course. So with this notation, we can write yr is equal to Ix divided by yc multiplied by a. So this is the location of our resultant force. We can find the location of xr. So xr being this quantity over here, so with respect to the y-axis. And without showing all the details, xr is equal to Ixy divided by yc a, where Ixy is the second moment of area with respect to both the x and y axes. Now these second moment of areas are widely tabulated for standard geometries. So here I included from a standard textbook for a rectangle, a circle, a triangle, what these moments of areas are. Now note that most tabulated second moments of area are with respect to the centroid. However, our second moment of area, which is defined as y squared, where y has its origin passing through the x-axis. So it is not passing through the centroid, but passing through a different axis. So what we need to do, we need to use a concept called the parallel axis theorem. Which states that if we are looking for the second moment of area about a certain axis x, it is equal to the second moment of area about another axis where we know its value. So here I'm going to call it IXC, which is the notation used in this table over here. So this is the second moment of area about the centroid, plus the distance between the two axes. So between the axis passing through the centroid and the axis where we want the second moment of area. And so that distance will just be YC. And so the second moment of area states that IX is equal to IXC plus the total area multiplied by the distance between these two axes. Okay, so let's visualize this. So let's say we have a rectangle that is submerged below a surface over here. Again, we've stated that the y-axis this is our y-axis here. Y is equal to 0 at the surface. This is our centroid over here. Therefore, this distance here is YC. So what this is doing, what this is saying, is that in the tables, our second moment of area is calculated about, so our IX that we are looking for, let's say for the rectangle over here, it is calculated through an axis, so IXC. So this is an x-axis passing through the centroid. And so our y-axis will be in this direction over here. So they're performing an integration over this entire surface of y squared dA, but where y equals 0 is located through the centroid. However, our second moment of area that we've derived here, our y is relative to the free surface. So what the parallel axis theorem tells us is that if we know the second moment of area at a certain location, so this is IXC over here, we can calculate the second moment of area about another axis, and for us that axis is this one over here, by saying that it is equal to IXC plus the total area multiplied by the distance between the two axes, which is YC squared. So for example, looking at our result for YR, what we would say is that it is equal to, so this IX over here is the IX about the x-axis, the free surface. And that is equal to our tabulated second moment of area about the centroid plus a YC squared, so this is our parallel axis theorem, divided by YCA. So this tells us that it is equal to IXC, the second moment of area through the centroid, divided by YCA plus YC. And this is the result that we are looking for. So the location where the resultant force acts is called the center of pressure.